Hello, Calculus and Vectors class. So we have some good news today. This is the very last lesson of the vector geometry portion of the course. But as usual with the good news, there is some bad news, which is that this is a bit of a longer lesson, so just be prepared. In fact, I'm going to break this up into two parts just to make this a little bit easier to digest. I'm going to recommend that you keep your mouse on the pause button and be prepared to pause from time to time, just so you can make a few notes. And really just take some time to absorb all the information that you're going to take in over the course of this video and the next video, which will take care of the second half of this lesson. So without further ado, let's jump right into the lesson. And the big goal for this is we're going to try and figure out if we have two planes, how they can intersect, and how to determine what type of intersection they have. So before we start dealing with actual equations and numbers, let's talk about the types of intersections. The first option you have is where we have two planes that are not running parallel to each other, and they're going to intersect as a line. And when we finish our solution is going to actually be an equation of a line in parametric form. Option 2 is where we have two planes that are coincident, and you're going to notice that they're running parallel to each other, and you're going to notice that their normals are also scalar multiples because they have to run parallel to each other as well, as opposed to option 1 where we had two normals that were running in totally different directions. So we can't have normals that are scalar multiples in that case. And option 3 is where we have parallel planes that do not intersect. We can call them parallel and distinct just to differentiate from the coincident option, which is also technically parallel. So when we have that option, usually I'm going to refer to it as parallel and distinct. Now, as I mentioned, the normals tend to be very important here. They give us a lot of information. And in fact, when we deal with two planes, we're going to start by examining the normals just so we can start narrowing down our options. You're going to find that with all these types of problems, all we're doing at the very beginning is narrowing down our options until we know exactly what type of intersection we have. So now that we dealt with all three types of intersections, let's start dealing with some specific problems. So example 1 asks us to describe how the planes intersect. So we have these two equations here, and we don't know really what to do with them, but we already said that if we examine the scalar multiples, then we can get some more information. So that's what we're going to do. So I've started here by writing out our normal vectors, which again is just our a, b, c values from our equations, and that tells us our normal vectors. Now looking at these, we know that we can't multiply normal 2 by some number to get normal 1. It doesn't work. If we multiply it by 2, the x's are going to work, but the y's aren't going to. So we know that they're not scalar multiples. So right away, looking at our three options here, there's only one option that has normals that are not scalar multiples, and that's option 1. So we know that they have to intersect as a line. If they were scalar multiples, we know it would have to be option 2 or option 3. So that's going to be the second category of solutions that we're going to deal with later on in the lesson. But for right now, let's deal with option 1, where we have two non-parallel planes that intersect as a line. So now that we've figured that out, now we need to start figuring out that line of intersection. Now, if it says describe how the planes intersect, if we can give a solution, we should. So now we're going to determine that line of intersection. So we're going to use an old trick, but it's something that's going to be very helpful here. We're going to use elimination. Now, to explain why, we'll take a look at our equations. And you notice how we have three variables here. Three variables are already way too difficult to work with, so we want to get rid of at least one of those. So I'll tell you right now, it doesn't matter which one you get rid of. Take a look at your equations and just figure out which one makes the most sense. In this one, it'll probably be equally easy to get rid of y or z because we have no coefficients, or a coefficient of one for both of them. In this case, we're going to pick z. So to do that, I've written out our equations as a system here, and we're just going to subtract them because that will get rid of our z's. So we subtract them, and the result of that is the next line, x minus 2y plus 0z plus 5 equals 0. Or we get rid of that 0z and we get x equals 2y minus 5. So not quite like our regular elimination, because usually we'd have x equals some number. But since we have two variables left over, we're going to get an equation. So it doesn't look super helpful at this point, but we're going to use one little trick to help us out here. Now think back to our understanding of parametric equations, because we said that's what we want our solution to look like. So we're going to start trying to turn this into a parametric equation. Now we said in a parametric equation we have a parameter, which we're going to call t for this example. That kind of is going to be our sliding scale that helps us to figure things out. Now the trick with t is that the value of t doesn't matter, so it can kind of go anywhere and it's going to work for us. So the little trick here, and you're going to see how this works in a second. I'm going to explain it as we go. We're going to take x, y, or z, and we're going to set it equal to t, whichever makes the most sense in this particular problem. And this one, because we have x equals 2y minus 5, if we were to just replace y with t, that would look like one of our three parametric equations. So that seems to work best for us right now. So we're going to set y equal to t. And then what happens is we take that equation that we found using elimination in step 1, and we're just going to replace our y with t. So what we've done now is we've actually created two of the three parametric equations for our line. So now the only thing left to do is to come up with a third parametric equation. And the way we do that is we're going to take one of the equations of our plane. Doesn't matter which one. In this case, I picked equation 2, which we just took from above, right up at the top here. And we've just written it out again. But instead of x and y, we're going to take our... Sorry, let me fix that really quick. So all we've done is instead of having x and y in this form here, we just replaced them with our two parametric equations. Instead of x, we've replaced it with 2t minus 5. And instead of y, we've replaced it with t. That's all we're doing here. Now you're going to notice now we have nothing but z's and t's. So we know that if we rearrange this, we could get an equation for z all in terms of t. So we do that. Next line, we get 3t minus 11 plus z equals 0. We're just collecting up our like terms a little bit, cleaning it up. And then we finally rearrange it so that way z's by itself. And we get this equation here, z equals 11 minus 3t. And again, hey, look, that looks like one of our three parametric equations. So in fact, when we combine that with our x and y equations, we actually have all three of our parametric equations. And we just summarize them at the bottom below. So using this method here, we found that x can be defined as 2t minus 5, y equals t, and z equals 11 minus 3t. Now, what I will tell you right from the get-go, just so when you're dealing with these solutions in your practice problems, the parametric equations for these can look very different depending on if you set y equal to t, or x equal to t, or z equal to t. It will also change based on which variable you eliminate at the very beginning, because that's going to dictate which variable you're going to set equal to t. So those two factors are going to play a big role in what your equations look like. And there are multiple different ways that you can represent this, because again, your t value is kind of a sliding scale, and it's kind of fluid. It doesn't really have to be a set number. So what will happen is if you have x equals t and you have two different y and z equations, you can still use any t value you want, but the point that you generate using that t is going to be different from the point that you generate using this equation here. But it will still be a point that's somewhere on your line. So it still works. So just be careful. Don't be alarmed if the result you get is not the exact same as the result that's in the solutions. Okay, there are different options for these. So hopefully you're good with that. Now we're going to go on to try some other types of intersection problems. So let's go on to example 2. It's asking again, describe how the planes intersect. So first step, we're going to examine the normals. Okay, so you're going to start by writing out your normals, your normal vectors, just by taking the coefficients from your equations. So 2, -6, 4 from your x, y, and z coefficients goes into your normal vectors. And this one, just by eyeballing it, we can see everything in normal 2. All the coordinates are just our coordinates from normal 1, but we just multiply them by 1.5, which we've written off at the side here. Normal 2 is equal to 1.5 times normal 1, which means that they are scalar multiples. So in this case, now we know, looking back at our options here, it can't be option 1, it has to be option 2 or option 3. They have to be parallel in some way, shape, or form, either coincident or parallel and distinct. So I've just written that down below. So we're going to write, therefore, parallel and distinct or coincident. Now that we know that, now we're going to try and figure out which one it is. So the way we do that, in this family of solutions, we're going to take our two equations and we're going to examine them a little bit closer. But to do that, because all the coefficients are different, it's not super helpful. So what we're going to do is we're going to multiply them so that way the coefficients are the same. So what I've done here, you'll notice I've taken equation 1 and I've multiplied it by 1.5. And what that does is that it takes all of our x, y, and z coefficients and makes them all the same. Now, our last step, we're going to take our d values and we're going to examine them. In this case, we have -10.5 and -2. Now, you notice at this point, they are not the same, which means that we're going to have two different equations. If you're not quite sure why that is, think a good analogy would be thinking about two parallel lines with different y-intercepts. It just means that they're going to be shifted up and down. The only difference here is that with 3D geometry, we don't really have an up or down clearly defined. So just think of it as a shift by about 8.5 units. So really, these are going to be two parallel planes that are shifted from each other by 8.5 units. So essentially, these ones are parallel and distinct. So we're going to conclude that at the very bottom. And that's the end. That's as far as we can go. We can't describe the intersection in any more detail. They're parallel and distinct, and that's all we can do. Let's try one more, just to see the third option here. But again, we're going to take this as if we didn't know what our intersection is. So we're going to start by examining the normals. We write them out based on our coefficients from our equations. And again, we notice that all of the coordinates from normal 2 are just double the coordinates from normal 1. So now we're going to say that normal 2 is equal to 2 times normal 1. So they are scalar multiples. So again, we know that they're going to be either parallel, distinct, or coincident planes. So again, now that we're at that stage, we're going to look at the equations and we're going to examine them again. And again, we'll multiply them so that way all the coefficients match, and we can see what's really going on here. So to do that, I've taken equation 1, I've multiplied everything by 2, and we get 2x plus 2y minus 42 plus 4 equals 0. In this case, we have the same d value. The equations are identical, so we know that they have to be the exact same plane. So in this case, plane 2 is equal to 2 times plane 1, so they're scalar multiples. So therefore, the planes are coincident. So hopefully this is not too difficult. Aside from the intersection on the line solution, which can be a little bit tricky, but make sure you do your practice there, the other two are not too difficult as long as you remember to examine your normals and then look at your equations of your planes to figure out what type of intersection you're dealing with. So hopefully that makes sense. Go do some practice on this stuff, and then come back and see the second half of this lesson, where we're going to deal with intersections of three planes.